Recording. Okay, so today we're gonna talk about groups of permutations, which is a directly fusion dance of chapters 5 and 6. So we're gonna talk about functions again, and we're gonna talk about groups again, but we're gonna talk about them combined. That's what we're gonna do. So, um, we're gonna confine our discussions to functions from a set to itself. This is already a hint that, wow, well, we know what also has that requirement? A group. In other words, we consider only functions that have this signature here, whose domain is a set A and whose range is in the same set A. To begin with, we know that any two functions f and g are equal, like extension equality. We talked about this before. And we're also going to note that in this particular scenario where f and g can be composed, their composition is going to look like this. And the composition of functions is associative, which is also another hint that, hey, this is the same as that. And then there's the proof there. And then by a permutation of a set A, we mean a bijective function from A to A. There is a one-to-one correspondence between A and itself. Okay, so bijective means injective and surjective. Injective means that each one of the elements in the domain are being mapped to different elements of the range. And surjective means that all the elements of the range are being used. In elementary algebra, we learn to think of a permutation as a rearrangement of a set of elements of a set. Thus, for the set 1, 2, 3, 4, 5, we may consider the arrangement which changes that to 3, 2, 1, 5, 4. This rearrangement may be identified with this function. And how do we know this is going to be the case? Because the function is bijective, which means that each element in the domain will be mapped to a different element in the range, and we're going to use all the range. So it is a one-to-one correspondence. So our elementary algebra intuition can be kept. That's good. The new definition, however, is more general, and because it's more useful. Sorry, it is general and more useful, because it allows us to speak of permutations of sets A even when A has infinitely many elements. Um, and in the previous chapter, we saw that the composite of any two bijective functions is also bijective. Thus, the composition of any two permutations of A is a permutation of A. It follows that we may regard the operation compose as an operation on the set of all the permutations of A. We have just seen that the composition is an associative operation. Is there a neutral element for composition? Because it's kind of the only missing piece of the puzzle, right? We have an associative operation, and we have
We
bijective
have the
functions.
inverses. We have
Sorry?
the inverses from the fact that those functions are bijective. So yeah, we're just missing the neutral element.
Yeah. So the identity function is the neutral element, and this is essentially battle cry thing about higher order functions, right? We're treating functions as elements now, which is, well, for us it's pretty normal, right? That's what it means to be a first class citizen. We're gonna say that the identity function is a neutral element. It's easy to see that the, what is this letter again? Epsilon
I'm pretty sure that's epsilon.
is a permutation of A, and then if F is any other permutation, then this holds. The first of these equations asserts that the composition with identity is just the other element for every element x in A, which is quite obvious since you can rewrite it like this. And then in chapter 6, we also saw that we saw that the inverse of any bijective function exists, and it is a bijective function. Thus, the inverse of any permutation of x is a permutation of A. Furthermore, if f is any permutation of A, then the inverse of f can be defined this way. And then we can also say that if you compose f with its inverse, you get the identity, which is this image. This is obviously true by the definition of the inverse of a function, and which means that the composition operator of functions qualifies as an operation in the set of all the permutations of A. The operation is associative. There is a permutation that qualifies as the identity element, and because f is bijective, we also know that there must be an inverse that can be defined in terms of the neutral element, which then does mean that the set of all the permutations of A with the operation compose is a group. For any set A, the group of all the permutations of A is called the symmetric group of A. And it is represented by the symbol SA. For any positive integer n, the symmetric group on the set 1, 2, 3, n is called the symmetric group of n elements, and it is denoted by Sn. Let us take a look at S3. First, we saw the permutations of the set. So this is essentially like, out of 1, 2, 3, how can we map these differently? So we can have identity, and we can have one that keeps the 1 intact and swap the 2 and the 3. Because again, the notation is that you start from the first row and you go to the second row. Well, you can imagine that those arrows are there. So these are all the possible permutations for 1, 2, 3. And then you can compose those permutations like this, essentially interpreting these as like maybe extensional way of describing a function. And then you can compose those matrices like this, and you can essentially like travel between using the functions. And the traveling actually matters because then you can have a geometric representation of that. So if you compose alpha after beta, you get this result, which is called gamma. Note that alpha after beta, beta is applied first and alpha next. That's why I read this as alpha after beta. A graphic way of representing this is just by using the arrows. The other combinations of elements as 3 may be computed in the same fashion. You can actually just do a Cartesian product of the compositions of those matrices, and then you can get this table. By a group of permutations, we mean any group S8 or Sn, or any subgroup of one of these subgroups. Among the most interesting groups of permutations are the groups of symmetries of geometric figures. We will see how much such groups arise by considering the group of symmetries of the square. We may think of a symmetry of the square as a way of moving a square to make it coincide with its former position. Every time we do this, vertices will coincide with vertices, so symmetry is completely described by its effect on the vertices. So if you have this square, for example, you can rotate the square, and when you rotate the square, you're actually moving the numbers. So if you rotate it 90 degrees, for example, you're going to have this rotation R1 here, in which 1 is going to go to the position of where 2 was, 2 is going to go to where 3 was, 3 to 4, and 4 to 1. So that's exactly what I just said. And if you want 180 or 270, those are the rotations you're going to be doing on them. For example, when we flip the square about axis, yeah, so there are other types of symmetries that come from something more complicated than just rotating it like this. You can also do
Yeah,
it like this.
yeah, you have rotations, but you also have reflections.
Exactly. Which is, well, rotating in another axis, right?
Not really. Actually, um, more properly, reflection is kind of like a half rotation.
Half rotation. I don't see it. You are doing this. You are doing a
Because
full
if you
360.
no. This is if you do two reflections, that's the same as some rotation generally.
You said true reflections?
Yeah.
Why are you doing reflection only halfway?
No. I mean, if you do two reflections in sequence, that's usually the same thing as as some rotation. Like for instance, if you reflect vertically and then horizontally, then that's the same as rotating 180 degrees.
Vertically and horizontally? Oh yeah, but then you are composing multiple reflections. I'm just saying that when you do a rotation like this, as I said, I'm doing with my hands, right? So, because when you rotate 90 degrees, the axis of rotation is inside the screen, right? But when you do it on X, the axis of rotation is the diagonal here. That's why you do it like this. You see what I'm saying? Do I have...
Isn't that backwards?
What do you mean by backwards?
Like when you do a 2D rotation, the axis of rotation is orthogonal to the surface.
Yeah, that's why I said going in the screen. It's
Ah,
I don't know.
okay.
Maybe it is because in college that's how we learn axis. I don't know. Maybe Tevo can help me here. When I was learning those things, we used going into the screen and things like that to describe which axis we are rotating upon. That's gonna be really, really unexpected. But the only way I have, the only piece of paper that I can properly describe this is by using a Yu-Gi-Oh card. So there it is. So when you are rotating 90 degrees, the axis is like here. So you're doing this. But when
Yeah.
you're doing on A, you were doing it this. You see. So that's the rotation I'm talking about. This is the axis. This is diagonal here.
Well, I guess you can interpret a reflection as a rotation on an axis that's parallel to the surface,
Exactly.
but then you have to invoke a notion of, okay, when you do that reflection, you're actually rotating through an extra dimension.
No, but the book is already doing that. It's already introducing the axis A, which is exactly this diagonal. The book is already invoking this notion. And that's why there's these dotted lines here. It's because it's trying to convey that you can do this, and this, and this. At least that's how I read it. Anyway.
I tend to think of that in terms of mirrors, actually. That's why I said reflection.
No, it is. We usually call this a reflection, but but to simplify in my head, I just say, man, this is just rotations in different axes because then it's uniform. Because if you think of mirrors, then you have two different notions to take care of. You have the rotation and the reflection. If you make them both be rotations, it's a single
Uh,
concept in my head.
Not really, because if you think of them in terms of mirrors, then a rotation actually becomes a derived concept. Like a rotation is just two
Well,
reflections in
that is
sequence.
true, but to me, reflection is more complicated than rotation. I rather keep rotation. Like
Well,
you
I
rather
think
have the reflection and make rotation out of it. I rather not have reflection at all and just have rotation.
well that's because if you think of it in terms of a 2D plane with numeric coordinates, reflections are actually simpler because that's just flipping the sign of one of the.
Oh,
Um,
you're definitely correct. In terms of the math, reflection is definitely simpler, but that's not how I visualize those things. Every time I'm talking about shapes, I try to visualize them in my head and usually in my hand.
I see.
Anyway, so you can also have the other, so in the same way, the other flips. So the other flips are essentially this and the other corners rotating as the axis. Our last symmetry is the identity, which leaves the square as it was. The operational symmetry is composition, which kind of means that you can, when you compose a rotation, you're actually just rotating it more. The net effect is the same as if the square has been flipped about its axis C. So again, as Marinho said, you can derive some operations based on other rotations. Or not operations, you can derive other configurations of the square. The 8 symmetries of the square form a group under the operation of composition called the group of symmetries of the square. For every positive integer above 3, because that's essentially like, you need at least 3 points to make a triangle, so that's kind of the reason. The regular polygon with n sides is a group of symmetries symbolized by dn, which may be found as we did here. These groups are called the dihedral groups. I don't know if that's how you call that. For example, the group of the square is d4 and the group of the pentagon is d5 and so on. Which kind of begs the question, how can you differentiate different kinds of d4s? Because a square is
You
a d4, a rectangle is a
you
d4,
don't because
the other
those
one is a
that
d4.
yeah, you don't because the square is the only regular quadrilateral.
Well, you do definitely because there's an exercise talking about rectangles. So there
But a
must be a reason,
rectangles
right?
but a rectangle is not a regular polygon.
Well, sure, but if it's not a regular polygon, why are we talking about the rectangle in the exercise?
Oh, because it's an exercise. But the point is, like, there is a group of symmetries for a rectangle, but it's not a dihedral group because a rectangle is not a regular polygon in general.
That makes sense. Every plane figure which exhibits, well, but there is the, I don't know in English how to say, the losango, right, or losangulo. That is also regular, but it's not a, well, it is a
It
square, but
is
there's a different name. So
no,
what do we do?
it only well, if you make it regular, then it becomes a square. So
Oh yeah, but then it's kind of weird why we're talking about that. It's square instead of the other name. Like seems arbitrary. But I guess you are right, right? So like at the end of the day, they're all squares and whatever the name. For example,
rhombuses,
sorry.
rhombi. Yeah, it's a rhombus. The how you call it in English. I'm not sure what the plural is though.
Okay.
Rhombuses, rhombi. I'm not sure.
For example, the following figure has a group of symmetries consisting of two rotations, so 180 and 360.
I've
Uh,
also heard it being called a lozenge.
okay, didn't know
Well,
that.
that word does exist. I think different regions, different English-speaking regions prefer different terms, I guess.
Yeah. Um, and true flips about the indicated axis, artificial or horizontal objects often have a surprising number of symmetries. But I'm going to talk with, this is also the case with the letters, so there's an exercise about different letters that we're going to be rotating. Um, I think the Z is kind of similar to this case, only 180 and 360. Far more complicated than the plane symmetries are the symmetries of objects in space. Modern day, okay, this is wild actually. Modern day crystallography and crystal physics, for example, rely very heavily on knowledge about groups of symmetries of three-dimensional shapes. Groups of symmetry are widely employed also in the theory of electron structure and of molecular vibrations. In elementary particle physics, such groups have been used to predict the existence of certain elementary particles before they were found experimentally. Symmetries and their groups arise everywhere in nature, in quantum physics, flower petals, cell division, and work habits of bees in the hive, snowflakes, music, and Romanesque cathedrals. Um, well, so there is a reason to start topology at the end of the day. It's not only because it's fun to have beautiful shapes to describe our stuff. Anyway, so 18 minutes. We have 42 minutes to talk about the exercises. So, exercise A. Is there any one of these that you guys want to talk about?
Not really. It's just filling out the things. It's um, not really that interesting, to be honest.
Yeah, I agree. Exercise B. Examples of groups of permutations. So in this one, you just have to write the table. Like this is just a manual process, and there's nothing really too much about it. And list out the elements of the cyclic subgroup. I forgot what is the definition of cyclic. Is that the one that has a generator?
Cyclic, yeah. If you have only one generator, that means you only use that. It's inverse, and you can derive the identity, right? Then you need to generate all of the possible elements from that.
So what are the elements of this one in this case?
Um, let's see. It's rotating the four elements on the left and flipping the two elements on the right. So I'm guessing there's going to be like 8 different ones.
It's rotating. Yeah, it's rotating the four first elements and flipping the other two. Yeah. Um, you said 8 elements?
Um, Actually, it could be less because it's a group of 2 and a group of 4, so they'll sync up. So it could be 4 actually. Let me think for a second. If you do,
Let's write
oh
this
yeah,
down.
there's,
I think it's gonna be educational.
let's do that actually.
Okay, so
Don't bother writing the top row because it's always going to be 1, 2, 3, 4, 5, 6.
yeah. Yeah, but which one I start writing here?
Okay, start with F and then like apply F to the result of applying F, and then you say okay, then it's like it's going to rotate one more space, so it would be 3, 4, 1, 2, and 5, 6, I guess.
Wait, the table here got screwed. Repeat, please.
Okay, so we have the F, which is 2, 3, 4, 1, 6, 5, right?
Yeah, we have the image of F, yeah. So it's
Then,
this, then
well, no, yeah, that's the, yeah, don't bother writing the top row because it's always going to be the same in
yeah,
all
no, sure,
cases.
but this is just for me anyway.
Okay. So, right, the result of applying F once is 2, 3, 4, 1, 6, 5, so it's the same as we already have, right?
Yeah.
The result of applying it another time would be um, it would be 3, 4, 1, 2, 5, 6.
3, 4, 1,
2.
2, 2, 5,
You rotate
6.
on every iteration. You basically rotate left the first four numbers, and then you rotate left the last two numbers.
Ah, okay, you keep flipping those around, right? So this goes there, and all of these walks left, and you also do the same
Uh,
with this.
yeah,
Pretty much.
basically.
Okay.
Um, that gives you 4, but then you also have to consider the inverse of F, if that's different from any of the ones up to the full rotation, which I think is 4 to the 4th, right?
Wait, let's count how many
F
we
to the
have. We
4th, I
have
mean.
we have this one for sure, this one for sure. How many times is gonna take us to go back to the beginning? So
4 times.
uh, one, then four is there, two, and one is there, and then two again. So there's three more, right? Aside from these two,
There are two more.
two more. Oh, I'm counting the same one twice. There's two more because there's one with the four and the one with the one in the beginning here, and then we
and then
restart with two in the beginning.
and then in theory, the inverses would just do that backwards. So I think we only have four states.
Four elements, you mean?
Yeah, four elements. Yes.
Uh,
Okay.
yeah, the
So
inverse would be you flip the 2 rows of F, and then you rearrange the columns so that the top row is sorted. Is that different from the ones we can derive? Let me think. So it would be 1 goes to 4, 2 goes to 3. Yeah, no, I think that's 1 goes to 4, 2 goes to 3, 2, 1, and then um, 5 goes to
oh,
6, 6
okay.
goes to
We want
5.
to see. Okay, let me see if I understand. What you're talking about the inverse is that we want to see what happens if like we
We
grab
want
this and we rearrange it going backwards, right? So one is here, two is gonna be one, three is gonna be two, four is gonna be three, 5 is going to be 6, and the other is going to be 5. If we have this second row in any of the permutations we already did.
Yeah. If we
I
do,
believe the answer is
then
yes, but
we.
we have to test it.
Okay, yeah, because if we do, yeah, we only have four elements total.
Yeah. Okay, educational. So I think we can skip now because, well, find a four-element abelian group of S5, write this table. You're gonna basically be doing the same thing. I just want to demonstrate, first of all, to check if I understand how to do it, and second, just for demonstration purposes. The subgroup of S5 generated by blah 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 has 6 elements. List them. Then write the table of this group. Very manual labor stuff. Okay, so exercise C. Exercise C. So any comments about exercise C?
Set of permutations. It's just a bunch of numerical algebra, I guess. um, and it's funny that we have to specify it's numerical algebra.
Yeah, it is funny because now we are doing algebra on functions, right? So it's very much required at this point. So we have to show that G is a subgroup of SA.
And write the table of G, yeah.
And write the table of G. So what do we have to do to make these proofs? We already have the elements of G, right? We have that. We know how many they are there. So we just have to write a table of all the possible permutations of this, right?
And yeah, we have to make the table, and then we have to verify that no matter how we combine the elements of G, we stay inside of G.
We stay on S of A.
No, we
in
have to
G.
stay in
In G.
G
Yeah, to
because
be a
G is a
subgroup.
subgroup. Yeah.
Yeah. Okay, then you have to do that for all of these ones. Okay, so exercise D, a cyclic group of permutations. So anything special that you guys want to comment on about this one?
Um, Not really. This is basically more of the same. We saw some similar things already in the what was it, 2 chapters ago?
Well, yes, but this is a little bit different, right? Because we have to. This is talking about permutations as well, and composition again. This is the same-ish but different, right? So prove that the composition of f of n and f of m is equal to that. So if you have a function f of m and then you compose that, yeah, it is the same as doing, well, you can demonstrate this, but this is pretty easy to demonstrate. The other one about the inverse, this is addition, so the neutral element is 0.
Yeah.
So that means that it needs to be, what is the
F of
inverse of
zero.
f?
F of zero is the identity, and the inverse is you just negate n.
You just negate n.
Yeah, so like the inverse of f of 1 is f of minus 1. Remember, n is an integer in this case.
Well, yeah, but if you compose f with its inverse, you need to have 0 in this case, right?
Yeah, because if you do f of n plus minus n, that's the same as f of 0, right? Because you're going to take x, you're going to add n, and then subtract n, so that just leaves you with x again.
Oh, wait, so it's not that the neutral element is 0. You also need to have to care about f of 0. That's what you're saying.
Yeah, f of 0 is the neutral element of this group using f of n as the elements, which is the group we make on exercise D3, right?
Um, let G be that. Prove that G is a subgroup of S of R. Yes. Prove that G is cyclically indicate the generator of G. Okay, but I'm trying to figure out. Yeah, no, this must be the same. Yeah, this must be the same. Is what you said, right? So it needs to be x minus n, the inverse, because then if you compose f, you have to compose f of 0 with the inverse of f of 0. Is that it?
Well, the inverse of f of 0 is also f of 0.
Oh yeah, I
Because
guess.
f of 0 is the identity element, so it's its own inverse by definition.
Yeah, what's getting me confused is that we have two numbers to take care of for each integer n. So x is going to be 0, that's fine. But in
No, no, no. It's not that x is 0. Like, f of 0 is the 0 element of this group that we're constructing. And then the composition of the f of n's for any two values of n, it needs to.
no, you are right. The neutral element is f of 0, but the function that we are doing it's because the elements are functions, so that's why I got confused. That is correct.
Yeah, yeah.
Yeah, so it needs to be x minus n. Yeah, you're right. Okay, cool. So exercise E. Any comments about that?
Uh,
Seems like the same thing again.
well, but this is involving multiplication, so linear algebra for the win, I guess.
This is the formula for a line. So this is the formula for a line. Okay, so symmetries on geometric figures. Let G be the group of symmetries of the regular hexagon. List the elements of G. There are 12 of them. Then write the table of G. Yeah. So I guess that is the case.
Yeah, 6 rotations, one of which is the 0 or 360 rotation, which is the identity, and then you have the 6 reflections as well.
Yeah, and that's why we have 12. So this is the beginning of that. So this is identity. This is going this rotation like clockwise rotation. This is jumping 1. And then you just have to go through the angles and then reflection and things. Let G be the group of symmetries of the rectangle. Yeah, again, rectangle, right? So list the elements of G. There are 4 of them. And write the table of G. The rectangle
Yeah, remember, a rectangle, the
is a
sides are
square.
parallel. Yeah, opposite sides
A
are
square is
parallel.
a rectangle.
A square is a rectangle, but a rectangle in general doesn't have all the sides equal, right?
Yeah, yeah. Yeah, but if you have 4 symmetries, it must be a square, no?
No, a square has 8 symmetries.
It's because of the reflections. I keep forgetting. So you have 180, 360, this, and the diagonals as well, right? Keep forgetting about that.
Yeah, that's basically it.
Oh wait, but there will be 4 elements. So which elements are those? We have 180, 360. We are missing 2 of them, right?
Those are the two reflections, the vertical reflection and the horizontal reflection.
So you're talking about flipping it like this, and you are also talking about flipping one of the corners.
Yeah, and the diagonals, there are no diagonal reflections because the sides are not the same length necessarily.
Oh, so it's only this and where's the thing? So it's this and this.
Yeah,
You cannot do this because it's not the same. This is not a square.
the vertices are not coinciding after you do that because the lengths of the sides don't quite line up because it's not a square, it's a rectangle.
Yeah, yeah, that makes total sense. Yeah, and then we have the letters. So we have Z, V, and H, right? So V has only 360 and 1 reflection, right?
Actually, Z, yeah,
No,
360 is the
V.
identity. Oh, V.
Yeah.
Yeah, V. Yeah, V only has one reflection.
Yeah, but you can also do 360. So it's one 360 and this.
Yeah, there are two elements. There's
Yeah.
the identity, which is the 360 rotation, or the zero rotation. It's the same
Yeah, but
thing.
now
And
Z, right? Z has 180, 360. Um, which rotations does this guy have? None?
well, it has two rotations. The reflections are kind of tricky, right? Because you can't really do a horizontal or a vertical reflection because that's going to change the
The diagonal is going to be pointing to the other
Yeah,
side.
exactly.
yeah,
It's
the
gonna be
diagonal is going to flip.
a mirrored Z. So there's only two rotations.
Can we make any reflections along the diagonal?
I don't like. I'm trying in my head, but I don't see how. Do we have three elements on the H? No, no, we actually have four because this can also do 180. So four elements on H.
Uh, you have one, two, the identity. Yeah, age is four, for sure.
Okay, I'm gonna bet Z is true. Actually, one, right? Because you cannot do a
No, you do have
oh
the
180 and
180
360.
rotation.
Yeah, okay, so it's true. Sorry. And oh man, and by the way, this exercise F4 here is just laziness. Couldn't he just make a polygon that is respecting these parentheses? What are we doing? That's so weird. Like you have the graphic, you have the LaTeX to make exactly this thing being the case because he needed to make this a parenthesis because looking at it the angles are not equal. Like what are we doing?
You would have to put that there regardless because, well,
You don't have to put that regardless. You just make it in the picture. You say that the length of this to the center is A and the angle is alpha and you make all of them alpha and all of them A's. What are we doing?
well, yeah, that's something you could have
And I'm
done.
not even complaining about the lack of that. What I'm complaining is that this is trivially not true. And if you're doing LaTeX, you can do this trivially about making this image at least look like the angles are equal. Because in here, it's obviously not. Weird.
Yeah, yeah, it's kind of weird.
Lazy stuff.
Yeah, can I agree that there are six symmetries in that odd, weird circle and move on?
6. So there's at least 4 because you can rotate it 3 times. And you can also do 360. And identity, right? So 4. So I'm missing 2. There's one reflection here. What is the final one that I'm missing?
Well, there are zero, and then one, and then two, and then the one is 360. Yeah, there are three rotations and there are three reflections, basically.
Oh, sorry, I was wrong. It's not 4 rotations. It's only 3. So
Why would there be four rotations?
because there's identity. Oh, but identity is and 360 are one and the same. So
Yeah.
it's the same. So 3 rotations. I can only see one reflection. What are the other 2 reflections I'm missing here?
You
Uh,
can you can reflect along any of the lines, basically.
basically, yeah.
Ah, okay. So here, here, and here.
Yeah.
I see. I see. Yeah, definitely 6. Yeah, but this is very useful, right? Because I don't know about you guys, but the intuition of enumerating all of these by hand is so like blurry to me. But when I think of the geometrical shape, it gets so much easier.
I do have a question though. Why did he make this circle when this is clearly equivalent to an equilateral triangle?
This is clearly true for any equilateral triangle.
Yeah, an equilateral triangle has the same symmetries, right?
Does it?
But then we
Yeah.
wouldn't have had the discussion about the funny circle.
That's well, we could have had a discussion about whether the triangle was really equilateral or not.
I don't know about what you said though, because if I'm trying to apply the reflections on the triangle, and the triangle is changing its orientation. It's not the same as what happens in the circle.
No, the reflections in the case of the triangle, they are along the three heights of the triangle.
Ah, okay, so you are grabbing here, here, and here, and you're rotating that. Yeah, it is the same. It is the same. But I think in here, I don't know, I prefer the circle, even though it's the same. And it's actually what Tevo said about the discussion of the lazy stuff. I think I would complain about that anyway, because if he cannot make these look like the angles are the same, who said an equilateral triangle isn't as much as big as a feet? Who knows?
Maybe the real reason he went with the circle instead of the triangle is because he's a hippie.
Okay. Consider the polynomial that it is unaltered when the subscripts undergo any of the following permutations. This is very unexpected that we are talking about changing the subscripts. And it's actually true because if you swap the first of these permutations replaces p by if you do swaps, you're only swapping 2 and 1, so it becomes like this, so the second member is the same. And this is exactly the same because it's subtraction, because this is a square, it doesn't matter if x1 or x2 comes first in the subtraction. So that's pretty cool. The symmetries of polynomial p are all the permutations of the subscript will leave p unchanged. They form a group of permutations. Okay, but in here, square, negative versus negative, and modulo are probably doing heavy lifting here, because otherwise you're not gonna be able to like naively change. Because if this is
E-
representing something, how can you just swap the subscripts? That's crazy.
Yeah, no, if you actually work through some of the exercises, you see that the ones down there have fewer symmetries because you have less ways to algebraically manipulate this thing to maintain the same value, right?
Yeah. Yeah. For example, one in well, ignoring the two being here with the three, right? But only by x1 and x2. If both of them are positive, they can be swapped, and if both of them are negative, they can be swapped. And if one is negative and the other is positive, the result is negative, and it's commutative, so it's also kept negative. So you can do tricks like that, but this is just because we are exploiting. Um, what is the term for that? There is a term for that, isn't it? When the known we are exploiting the known injectivity of those operations. Is that how you say that?
Uh, I guess another way to look at it is okay, what are the valid ways that you can do alpha remaining using the same symbols, I guess?
Well, that is a very lambda calculus way of going about it, but yes, that is true. Uh, okay, so H, properties of permutations of a set A. Let A be a set, let G be a subset consisting of all the permutations of F, or permutations F of A, such that uh, F of A equals to A. Prove that G is a subgroup of SA. Any exercises here that we are interested in?
I actually spent quite a bit of time thinking about 3 and 4 today, and I couldn't come up with an example for the 4, actually.
Okay, so exercise 3. Let A be a finite set and be a subset of A. Let G be a subset of A consisting of all the permutations F of A, such that F of X is contained in B for every X in B. Prove that G is a subgroup of S of A. Uh, of all the permutations F.
Yeah, basically the intuition here is you have a big set with a smaller set inside of it, and you are trying to look at just the permutations where the small set remains the same, right?
You're
Like if
saying that the
you
permutations that means applying F keeps you in B.
yeah, if you apply F to something that's in B, you stay in B.
Yeah, sure.
Um, and then like this is not really that hard intuitively. But then 4 goes on and says, okay, now give an example to show that 3 is not necessarily true if A is infinite. And it's like,
It's probably because we need to go. My intuition is telling me that we need to go on 3 about what happens if B is A, and then what happens if A is finite, if this breaks the proof, and in 4 making B A is a problem. I think it's something along those lines.
um, I don't think that quite works because if B is A, then trivially every permutation of A is a permutation that stays in B when you apply it to B.
Wait, repeat that?
Like, if B equals A, B is a subset of A that happens to be equal to A, then trivially, every permutation of A is also a permutation that stays in B when you apply it to B because A and B are equal, right?
Yeah, yes. But is there any? Is there? Well, that also proves that you're talking about in the case of 3, right? But what if A is an infinite set?
I don't see how that changes that.
Uh, what introducing A being an infinite set changes anything? That's the question. Hmm. There's no hashtag on this exercise though, so there's no solution for it. Dave, do you have anything in mind?
I do not currently know.
Here's the thing though. If A is infinite now, B can also be infinite, even though it's a subset, and it may be different than A.
Yeah, I was thinking something along those lines. Maybe in the case where A and B are both infinite and B is small is not A, like B is different from A.
Yeah.
Maybe there are some cases where trying to compose or trying to find an inverse for a permutation that stays in B will actually take you to A or something like that. That's the road that my intuition tells me I should go to try to find an example, but yeah, I spent some time thinking about it and I couldn't come up with any.
Crazy stuff. Yeah, but the exercise 3 makes a lot of sense after you said the way that you said. And I'm also having a hard time understanding what happens, what changes if A is now infinite. I could deduce that, okay, B can also be infinite and not be A. For example, if A is integers and B is only the even numbers, then that's fine. But what happens with their composition? How can I guarantee I'm going to stay in B? Actually, it's the opposite question. What makes me believe that I will not stay in B because it's infinite? So that's weird. And then finally, exercise I, which is kind of creepy. Kind of creepy. Yeah, so we are talking about, um, how should I say, a general framework of understanding anthropological research. So apparently that's how those people, those anthropologists look at us. So the entire population of the society is divided into clans, and I believe the word chosen here, clans, was meant to convey that we're talking about something that can be a family, but can also be like friend groups or I guess
It can be, yeah, it
guilds
can be
back
some,
in the day.
yeah, it can be something like larger than just a family, right? It could even be like pieces of a bunch of different families that happen to be together in a clan. Um, yeah, it's kind of like, yeah, it's not necessarily a family. It's maybe something a bit different, maybe something a bit more
The
complicated,
thing
right?
that makes me sense that made sense to me, it's a guild, like Victorian time guilds. That's what I thought when I read this the first time. Every person belongs to one and only one clan. Let us call the clans K1 to Kn. In every clan Ki. Okay, but here's the first question. Okay, this is just a generic framework, right? We are not supposed to have answers to all of those questions that I'm about to make. But my question is, what defines one person to be in that clan then? If you cannot be simultaneously at the same one and at the same time, well, at different ones at the same time, what is the criteria to be used to define that you are in K7?
Well, it depends on who your father is.
Well,
And it also depends on the structure of that particular society
well, no, but
because,
that's the recursion, right? I'm talking about the base cases of that recursion. We're gonna
yeah,
be
I
talking
got.
about this here, and I'm like, in the beginning of times, who said you were K7 and you were not?
Yeah, that's a good question. That's a very good question.
And here's the thing. This also is very anti-modern in a way because it's essentially disallowing pluralism. Because we like to say that you are multiple things at once, right? You are the son of somebody, and you're probably going to be a father of somebody, and you're going to be a friend of somebody else, and you're going to be the co-worker of somebody else. So we have the intuition that you should be able to be allowed to be in multiple clans at the same time. But this is saying no. There is a fundamental criterion here. In every clan Kai, all men must choose their wives from among the women of a specified clan Kj. We symbolize this by writing that the wife function receives a ky husband, and it is equal to the um, to her clan. Men from two different clans cannot marry women from the same clan. That is, if those two are not the same, then the wives are not the same.
Oh, that's just saying that W is injective, right?
Yes. No, but that is the older way to look at it, right? That's what we're going to be doing the exercises. This is more about like trying to fit in the framework, right? So two different men from two different clans cannot marry women from the same clan, which is also wild to think about. All the children of a couple are assigned to some fixed clan, so if a man belongs to clan Ki, all his children belong to a clan which we symbolize by C of Ki. Sure. Children whose fathers belong to different clans must themselves be in different clans. Like, again, it's very creepy to think in this way. There's so many implications that comes from these premises. So that is, if they are not the same, yeah, again, injective, right? So C is injective, W is injective. A man cannot marry a woman of his own clan, which sounds sad, but okay.
Well,
Uh,
no, this is just saying no incest, basically.
well, but we don't know what a clan is. Like, this can be anything. I just said family, but it could be something else.
Well, given the way that they are defined here, based on the clan of the parent, there are clearly some kind of familial ties within a clan. It's just that they may not necessarily be the ones we are used to.
It is a weird family structure because it means that every son of a family needs to marry wives from another given family.
Yeah, I found that weird as well.
Wait, repeat the implication there?
Rule 2 means that every son of a given family needs all of them to marry a wife from another same given family.
Another same. Wait.
Yeah, like let's say there are let's say there are clans A, B, and C, right?
Sure.
So it doesn't really matter what clan your father is from, whatever C happens to be, as long as all the kids have the same father, then they will belong to the same clan, right?
Sure.
That means, since the choice of wife is also based on the clan, because all of the kids have the same clan, then all of their wives will also have the same clan, which is weird.
I'm not getting the plot twist. Well, the conclusion of
Like,
that.
if you're from family A, you can only ever marry someone from family B, basically.
Ah, it's because it spreads. That's what you're saying. If my brother marries a wife from family B, all the other siblings are fucked. That's what you're saying.
They all have to marry someone from family B, and they cannot
Exactly. Yeah.
choose someone from another family, basically.
Yeah. Okay. Yeah. No. It spreads. It's like IO. It's done. Once IO is in, you're done. And once,
Actually, this is fixed, right? For all of time, actually.
well, we don't know what is the criteria to make it fixed, right? It could be the first one. It's just saying that it is going to be fixed, but what's going to be the criteria to make that happen?
No, it's tradition. Like, people from family A always married people from family B. Therefore, people from
Ah, okay,
family
okay.
A
So,
will
okay, even
always
in
marry.
my case, if it's the first son doing the thing, it must be the first son of the first generation of the thing. Yeah, I see, I see, I see. Yeah, I see what Teva said now. Now let K be the set of all the distinct clans. By true, W is a function from K to K, and by for, C is a function from K to K, and both of those functions are injective. Well, which is what's saying here. So that means that W is a permutation of K. Let G be the group of permutations generated by C and W. That is, G consists of C, W, inverse of C, insert inverse of W, and all possible composites which can be formed from these. Clearly, the function epsilon is in G, since that can happen. Here are two final assumptions. Every person in any clan has a relation in every other clan. This means that for any chi I and chi j in K, there is a permutation alpha in G such that if you apply that, that's not really that surprising, right? Having a relation, like a relation can be whatever. Rules of kinship apply uniformly to all clans. Thus, for any alpha and beta in G, if they are the same for some specific clan Kj, it is necessarily follows that everybody must have that relationship available as well. Well, and like the equality also spreads, right? So if the relation alpha and the relation beta are the same for a particular clan, all the other clans must obey that. Which is also weird, right? This is also very weird. Uh, okay, cool. Okay, so exercises. We need to prove parts 1 to 3. Let alpha be in G. If alpha of ki is equal to ki for any given ki, then alpha is equal to sigma. So this is essentially saying that the only relationship available that can go from us to ourselves, from a particular clan to itself, is the neutral element. There
This
will not be
follows.
any other one.
Yeah, this follows pretty much directly from 8,
Um,
which is the last one that we just saw. That rules of kinship are uniform, right?
well, but I think that's not, that doesn't, I don't see that as what you said
There's
holds. Go, Tiv.
there's also the fact that you cannot marry people from your clan, so if that holds, then that's you.
I am confused. Relation is unmarried, so I don't know what Tiv was talking about. And I think what Marinho said doesn't go all the way, because this is saying that if you have this, you cannot have alpha being anything else than epsilon, and that's what I'm. How are we going to prove that?
Oh, this
There
follows
cannot
from
be any
8.
relation. There
You
cannot
This
be any
cannot
follows.
relation
marry.
that follows this that is not epsilon. How can you going to prove
This
that?
follows directly from 8, Lemos.
You cannot marry people from the same clan, and your children cannot be in the same clan, which means that there will not be any permutation where you can have one element that maps to itself that is not the identity.
Alpha is not marriage. That's what I'm trying to say, Tiff.
It's a composition of marriage and childhood, I
It
guess.
isn't.
It's a
It is a
composition of,
relation. It can be anything.
Well,
but a relation is a permutation, a composition of C and W and their inverses.
A relation is a permutation of CW and their inverses.
It's a composition of C, W, and their inverses.
That's not written here.
It
But,
it
is.
is 7 actually. No, it's actually, yeah, it's the point between 6 and 7 actually. Where we're defining G, you see? Let G be the group, blah, blah, blah. It's generated by C and W, yeah.
no, it is written in 7. There is a permutation alpha in G. And because of what Tevo said, the relation here must be some sort of marriage relation. And then it does apply that you cannot marry people from your clan. And then yes, then it holds that alpha must be epsilon.
Yeah,
I don't think
you
8
can
is
prove
enough
from
though. 8 is not enough.
no, 8 is enough because what happens if you instantiate beta to be epsilon?
That's fine, but that doesn't prove what this is asking us to prove.
It does because it means, okay, if alpha of ki equals epsilon of ki for a specific clan, in this case ki, that's the given from point 1, right? Then it
Yes?
necessarily follows that alpha for any clan is equal to epsilon of any clan, therefore alpha is equal to epsilon.
No, that's what I'm trying. Maybe I'm confused. What you said doesn't prove that alpha must be epsilon. How can you
It
prove there
does.
is not a
It
gamma
actually
that can do the same?
it does because the relations are uniform. Like if it does a thing to a single clan, then it
Let
means
me
that it
write
does
this
the same
down
thing
because
for
I
every
think
clan.
either I'm not communicating it properly or actually that must be it. I'm not communicating it properly. So let's say, right? So let's say that there is a gamma relation that also is this. Let's just suppose that. Let's suppose that.
Then this relation is also equal to epsilon.
Let's suppose this. First of all, what my question is that I think this that you can only use 7 to prove what Tevo said to prove what I'm about to say is, how can you say that this must also always be true? That's my question.
Because that's what Rule 8 says.
No,
If it
Rule
is
8
true for
says
a single
that if
element,
this is equal to this, that this is what 8 says. I don't know what you guys are talking about.
yes, and then if beta is the identity, then it means that gamma needs to be the identity.
no, you guys are assuming it is identity. I'm not. Your sentence is started by saying, if alpha is identity, then this follows. I'm trying to.
No.
I'm not starting with
No,
that argument.
I'm just using the 2 points from the point, like the assumption from 1, the exercise 1, and the rule 8, okay? The assumption from exercise 1 is alpha is identity at a particular ki. That's the assumption from 1. And then the rule from 8 is, okay, if alpha for some k is equal to alpha of some k is equal to beta of the same k, then it follows then that alpha of an arbitrary k is equal to beta of that same arbitrary k, so alpha equals beta, right?
Which doesn't mean that alpha is epsilon still.
It does, because alpha of ki equals ki is equivalent to saying alpha of ki equals epsilon of ki.
No, that doesn't. Okay, that is the confusion that I think I'm getting. What you're saying is true, but we already have seen in previous chapters functions that can work as identity, but they are not identity.
But we have this additional rule 8, you see?
No, I
We
don't
don't have
understand
that in
how
other
rule 8
contexts.
mandates that alpha must be epsilon instead of an arbitrary gamma. That's what
It's
I'm
not
trying to
just
say.
rule 8 by itself, it's rule 8 plus the assumption from 1 that alpha of ki equals ki.
Yeah, I am. Yeah, I think I'm not getting my point. Well, I'm not understanding how this proves that alpha must be equal to epsilon if there supposedly a particular gamma that is not epsilon that also makes this true.
But there
But
cannot exist
that is
another
what I'm
gamma
trying
that
to
is not
get
epsilon.
on, Tiv. How can you prove that? I think you must
By
use your argument to prove that.
uh no, it follows from rule 8, from what
Yeah, I don't
Marina said.
understand. I don't understand. How can you prove that there won't be a gamma that also makes this holds?
It's because we're taking 8 as a ground truth, and doing what you say directly contradicts 8.
What 8 says is that a gamma would have to be applied to every clan. Doesn't mean a gamma
Mm,
is epsilon.
No, no, no. It means for any alpha and beta, no matter what they are, if they are equal at one point, then they are equal in general.
Yeah, maybe I'm not getting my point across, but okay. Well, I think what Tevo said before, like about no, you cannot marriage people from the same clan, is what makes my gamma hypothetical gamma be equals to epsilon. But maybe I'm wrong. I don't know. I'm actually gonna write this down to take answer to ask to try again later. So how can I know if I have a gamma that also does the same? How can I prove that this must be equal to epsilon? Okay, so exercise G. So is there any questions about exercise G? No, not G, true. Let A alpha G, there is a positive blah 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 such that, and then the explanation of what the exponent means. It means composing a bunch of functions together, right?
Right.
It's essentially saying that if you compose alpha m times, and that's going to be equal to epsilon.
Uh,
That is interesting. M factors of alpha.
it if every clan is connected to every other clan by relations of marriage and childhoodship, then it means that there are no cycles between, like there are no closed cycles, which means there is a function. Uh, there is such a function that you can use to walk every member, every clan, such that you get to the original clan, and that M will be the same for everyone. Actually, I that doesn't necessarily prove it.
So this is essentially saying that if you apply alpha function, alpha relation many times, m times, you're gonna eventually go back to square one.
Uh, there is an M where applying alpha M times will go back to square one for every clan.
Oh, but then that proves it, no?
Well, that is the assumption. We have to prove
No,
why
no.
that
Okay, so you're
exists.
just repeating what I said. I thought you added something in there.
mm,
And intuitively, I think that follows from the fact that you can navigate from every element of every clan to every other clan by a composition of functions, but I'm not sure how to state
Oh,
that
but it must be the same
formally.
function. That's kind of the problem.
Yes.
So you have an alpha, and we know alpha must be generated out of C, W, and their inverses. We know that. And we also know. Mm,
basically, we need to prove that if you compose C with itself, at some point you're gonna get epsilon, And also that if you compose W with itself, at some point you're gonna get epsilon. Um,
I don't think that's necessarily the case, Marinho, because alpha can be any of the permutations of the compositions of those four. It doesn't need to
yeah,
be
then you have.
sub or W necessarily.
Well, yes, but you need those building blocks to then prove that okay, any composition of C and W and its inverses eventually goes back to identity. I guess
In M
is the
steps.
yeah.
So how would we go about that? By the way, given this time that I'm thinking about what I wrote here, um, I think what Tevo said before, that like, if you have a gamma that does that, isn't that gamma just epsilon then? I think you said something like that, right, Tevo? Like let
Actually,
go on,
that
Tevo.
was Marinho's point, which follows from rule 8.
No, but that's not what I said. What I said is that even like back to point one here, um, and I'm trying to establish that I may have a gamma that if applied to Ki also goes to Ki. But I'm trying to make I'm working on the assumption that this gamma can be different than epsilon. And what I have to prove is that it must be equal to epsilon. But if I have a such gamma that when applied to Ki go back to Ki, how can this not be epsilon? That's kind of my what I'm getting at. This doesn't come from point 8 at all because gamma is following point 8, right? But I'm trying to go, as I said, I'm trying to go back to the point that I cannot make such gamma different than epsilon. And I'm trying to think, if I have such function that if I apply to Ki is always back to Ki, how is that different than epsilon anyway?
Yes, it follows from the rules of wifeship and childhoodship as well. But it also follows from rule 8, which was what Marina was trying to say. You can go
No,
both ways.
man, Luru 8 is about having two Greek letters that spread around all the clans. That's it. And if I have a gamma that does this, gamma of Ki goes to Ki, I have rule 8. That's what I'm trying to convey is that you guys are
Uh,
jumping to the fact that gamma must be equals to epsilon. Uh, Rule 8 is about just the spreading.
no,
That's
no,
it.
no, no. Rule like how can I say this? If
But I think this must be true. That's kind of what I'm getting at. I think I cannot make a gamma that is not epsilon in this case.
It
So
must
I'm
be
gonna be
true even if
specific.
you don't have rule 8. Yes, if that's what you're trying to say.
Exactly. If you work, like even ignoring the spreading, assuming the if that Marinho also said it's important, and I agree. Even if you try to make another Greek letter that follows this property and that the alpha and the gamma spreads around the clan, the conclusion must be that gamma must be equal to epsilon. Like let's write that down. If you have an alpha of a ki that is equal to a gamma of the same ki, which in this case happens to be equals to ki, this being true for all the clans is following rule 8. That's it. That's rule 8. The problem is that we need to prove that this must be equal. That's not the correct symbol. This must be equal to epsilon. The fact that it spreads doesn't matter from what I'm trying to understand. That's why repeating that is rule 8, it was not convincing me. But the thing of the matter that I think now I understand is that if you have this property, if you have such property, how can this not be epsilon?
because that's not a for all in one. That's a sum and exists.
It exists. Could you repeat that?
Like if A of Ki equals Ki for any given Ki, that is, if there exists some Ki where this is true, then alpha is equal to epsilon by applying rule 8.
If alpha of ki is equal to ki, repeat the second part again, please.
Like the premise from exercise 1 is there exists some ki such that alpha of ki equals ki. And it's asking you to prove alpha equals epsilon from that. Plus the assumptions we had above, right?
Plus assumptions we have above. Yeah. I don't know why you guys are talking. I'm still not understanding why premise 8 participates in this discussion at all. Because the fact that it spreads to all clans doesn't mean you need like
No, it's
how is that
because
related to epsilon? That's what I don't
you could
understand.
conceive in general that there may be a permutation where some element is a fixed point of that permutation, right?
Sure. Yeah. So it's its own inverse.
No. There is some element where if you pass it through the permutation, it just stays where it is.
Yeah. Sure.
Like you could think of that existing in some group of symmetries, but rule 8 here says, yeah, no, actually, if you have, actually no, that's not really rule 8. It's it basically lets you generalize that, okay, because this is a fixed point at this particular element, then it must be a fixed point in every element, which means it's just identity.
Okay. So what you're saying that you are using rule 8 for is that because you know it, you found a fixed point of a particular element, you can generalize it because of rule 8 to every other k, and then that is just
And that,
identity.
yeah, basically.
Hmm. Okay, so are you saying then that every arbitrary permutation that receiving a ki is equal to ki must always be equals to epsilon because
Only
of...
if you have rule 8, yeah.
Okay, so essentially this is giving you like the base to use this as a generalization, and that is why you're saying that if you generalize this process to everybody, then it must be identity.
Yeah.
I think I finally understand why rule 8 matters for this argument. Yeah, I think I'm understanding why it matters. Um, but wait, but did I get my point across? Did you guys understand what I was trying to talk about? Or not? Or is it
You
still
mean the
not clear?
fact that you can prove this by the other rules as well without
No, the
taking.
point across that what happens if I have an operation that is not epsilon, but also maps ki to ki?
Well, yes, if you were not in this framework where rule 8 exists, then you would just say that, okay, those two things happen to have the same fixed point.
No. That is also correct. But Tevo, here's what I was trying to convey before. I think what Marinho explained, I can explain it better what my confusion was. What we're trying to say is that if this is equal to this, then alpha must be equal to that. I was working under the assumption that there may be another operation. Oops. There may be another operation that is not, let's use beta here. You have an operation that is not this, but that also has this property. You see? And I was trying to understand this. How can you say with confidence that beta must be equal to epsilon? Like, this assumption must be wrong. And what Marinho explained is that this gives you, like, even if you work through this thought process and say, okay, you have a beta that is not epsilon, but it follows this property. The answer is it cannot be. Because rule 8 is saying that if this holds for one case, it must hold for everybody. And the case that holds for everybody must be epsilon. Hence, this is impossible to beta to be different than epsilon. You see?
And just to make it clear, what happens if you get rid of rule 8? If you look at the examples of symmetries for shapes that we were looking at before, like clearly the diagonal reflection of a square, it keeps point 1 at point 1, but it's not identity, right?
Yeah, no, exactly. But that would be an example of something that behaves almost like identity, right? But because you have rule 8, you know that all the points of the square must follow the rule. And when that premise is included, the flipping of only like a few corners staying and the other ones getting flipped is denied. That cannot happen.
Basically, yeah.
Then it follows that this premise that beta is different than epsilon must not hold. And then you directly prove that alpha is equal to epsilon. So um, it matters, the spreading matters, going back to my original point that I was not understanding why you guys are bringing it up. It matters because it allows you to say that this is for not only a particular ki, but for all of them, which means that this premise here is impossible to hold, essentially.
Yeah, rule 8 basically lets you turn an exist into a for all in some situations.
And again, sorry that it took me a while to understand. But you guys know I'm dumb, right? So there was a disclaimer already. Okay, exercise 2, we don't know how to do that, right? That's what I'm understanding.
I think you may be able to get to it if you actually write out. Like, I think we may be able to figure out a strategy to prove it if we actually make an example. Make an example symmetry group that follows these rules, write out the table for the elements, and then try to figure out what principle forces this to be true.
Well, let's try to do this intuitively because there's no boundaries for M, neither for M or N. So what if we say, okay, let's establish the intuition
Then,
of C and W are. What do they are?
well, there are bounds actually for n.
They are bounds for N. Isn't it just an integer, a positive integer? Where is it saying the bounds of N?
Um, it's after rule 6. You see now let k equals blah 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 up to k of n. So n is actually the number of clans.
Oh, okay, so M is a number that is smaller than the number of clans we already have.
Could be equal to the number of clans as well. Yeah, but up to the number of clans,
No, but if it's
like
if it's up to equal, that I think that's already fine for what I'm trying to do. So what are the intuitions of these functions? So C and W. So the W gives you what is the wife's clan of a particular husband in a particular another different clan.
yeah,
So this
given a
gives me
clan
this gives me
which
this gives me my clan based on my husband's. The W, sorry, and the C gives me the
the
clan
clan
of
of a
myself
child
based on my
based on the
dad.
clan of the father. Yeah.
And the inverses of that is probably going to be the clan of the child. Um, given the clan of the child, what is the clan of the dad? And the W is what is the clan of the husband given the clan of the wife. So with these four operations in mind, can we imagine a permutation? Okay, so if we apply C to inverse of C, we get to the same point, right? Can we intuitively imagine that all of these four, at up to the max amount of clans available, can we get to the same place where we started? That's the question.
Um,
I'm having a hard time understanding why the number of clans matter.
well, one of the rules. Let's actually start from the bottom. So one of the rules is you cannot marry someone from your own clan, right? So there must be at least two clans for this to make sense, right?
Yes.
That means two is the base case. So if there are two clans, then what are the possible ways to assign C and W, right? Well, there's only one way to assign W, which is you go from one clan to the other, right?
Yes.
And then there are actually two options for C. You can either say that C equals W, or that C is the identity, basically.
Yeah. Makes sense.
So if you have an arbitrary alpha made up from C and W, um, then if C is the identity, then um,
M is 1, N is 2, everything is fine.
well, if C is the identity, then if alpha happens to be C, then M is 1. Actually, M is 0 because, well, actually no, that's the trivial case. If M is 1, yeah, because if you just apply C once, that's the identity, so you're already back where you started. And if it happens to be W, then
M is true.
M is 2 because you can go to the other clan and then
And then go
back.
back. Oh, but that's for this like the case of 2, right? Uh, and we have to consider the combinations, right? We should be able to pick any, because here's the thing. The parts 4 to 9, when we are way exceeded our time, we have to explain those things. And there are some operations such as these, right? That is possible to alpha to b. And then can we also prove that in less than n steps, or up to n steps, you can go back to where you were?
Well, in the two example, then the number of C components that exist in the, well, if C is identity, right? If it C is not identity, then C is equal to W, so the argument holds regardless. If C is identity, then composing C with anything else doesn't change that anything else. So whatever number holds for the
Yeah, no,
other.
you are right in your example. I'm saying that alpha can be this shit.
Well, no, but alpha must be constructed from a composition of C's and W's, right? And their inverses.
Exactly, and this is one of them, right?
Uh, well, that's just identity directly.
Well, it's because this thing is associative, right? But yes. But what I'm saying is that there is an arbitrary combination of C's and W's and their inverses that doesn't necessarily. Actually, that's not true. It will always be one of those four because you can associate them in a way. Oh, but this doesn't commute, right? So this means that if C1 and W were swapped in here, then what is this? You see what I'm saying?
This doesn't commute. Yeah, because the child of the husband of the wife of the father is not the same as. Actually, could you prove that those commute? That would be potentially helpful.
No, if they commute, then it's easy because you just rearrange. Because imagine an arbitrary permutation, right? So an arbitrary exponent here. It doesn't matter what alpha is because at the end of the day, you can always rearrange the terms to negate them. We already did an exercise with this before with the abelian groups, as far as I remember. So you rearrange them to negate, to make them identity, essentially crossing them out, and you're going to end up with either like C, W, or their inverses, or a combination of the W with the inverse of C, or C with the inverse of W.
Yeah, intuitively, I don't think you can make those commute in general, unfortunately.
Yeah, exactly. I'm going all by intuition. I haven't proved this, but I don't think, because initially you kind of want to, given that you know that this is a permutation, you know that the types will match, right? If you swap the two functions, the input type and the output type, they are always the same, so you can, but the semantics are completely fucked if you do the swaps.
Yeah.
Anyway, so let's try to finish this. So the group G consists of exactly n permutations. The group G consists of exactly n permutations. So how can we prove this one?
Uh, I would try to sketch a proof in the direction of if the number of elements is different from n, that would have to contradict one of the premises.
Okay. And then there is a okay. So then the author probably said thought to himself, "Man, this is gonna be hard. Only explain. Don't prove anything." If a person belongs to clan Ki, that person's father belongs to clan inverse of C. Um, yeah, we saw this is essentially the semantics of the inverse. If a woman belongs to clan Kj, her husband belongs to clan inverse of W. Yeah, what is there to explain, right? Well, I guess we can explain because if you compose C with this inverse, and what is C? What is the clan of the child? Um, what is the clan of the child, right? So given
Given the
the
claim of the
fathers,
father, yeah.
the clan of the father. If you compose what is the if you grab that clan, right, of the child that is based on the clan of the father and you apply to C minus 1, we know that's going to be equal to identity, which means that you are where you started. But this means that this must be a function that gives the clans of the child you get the clan of the father.
Yeah.
That's it. If any man is in the same clan as his son, then C is equal to epsilon. Well, this comes from the definition of C, right? Because C receives as input the clan of the father and gives you the clan of the child. But if that is equal to the same K, and because of rule 8, then C must be equal
It
to
must,
identity.
yeah.
If any woman is in the same clan as her son, same argument, right?
Same argument, yeah.
Because if the woman is in the same clan as her son, actually this is a little bit more intricate because we have to use the father as the bridge. So W is a function that you can get the clan of the wife given the clan of the husband. But we also know that the clan of the child is also the same as the woman. Um, so that means that they received the same input and got to the same output. So C is equal to W because of her weight.
Yeah.
If a person belongs to clan Ki, the son of his okay, the son of his mother's sister, so that your cousin,
Yeah.
belongs to the clan this thing. Um, okay, so let's take a look. So you first get you get the clan of your dad, then you have the clan of your mom,
Which is the same
then
clan as her sister, right?
which is the same clan as the sister. Why is that? Which rule is that?
Because your mom's sister, it has the same parents, right?
Ah, that is because of rule 4. Okay, so you have the clan of your aunt at this moment. Then you reverse W, which means that you have the
The clan of your
clan
uncle.
uncle, and then you apply C to it, which is gonna be the clan of your cousin.
Yeah. But this is just identity, so it's the same clan as you.
uh,
And
yeah,
rule, what was it? Rule, one of the rules said you can't marry someone of the same clan, so
yeah,
yeah.
yeah. This is rule 6, I think. Conclude the marriage between matrilateral parallel cousins. Marriage between a woman and the son of her mother's sister is prohibited. Well, which is what Marinho just said. Marriage between a man and the daughter of his father's sister is prohibited. So a man and the daughter. So you are her uncle, right?
The daughter of his father's sister,
Oh wait.
so it's his cousin.
Well, same argument as 6. Um,
Yeah, it's not quite the same function, but they cancel out in the same way. So yeah, this a very similar argument to 6.
Wait, it's not the same function.
Yeah, because it's a man and the daughter of his father's sister. So you start with the man, right? Then actually you have to start with the
No, you have to start with the inverse of C as well, because you have to get the dad of the both of these guys.
yeah, you have to get the dad of the man, right? And then you get the sister of the father is in the same clan as the father, right? And then you do the child of that sister. So you have to go to the
C.
husband.
Oh, you have to go to the husband. You're right. Well, then you have the beginning is exactly the same, isn't it? C minus 1, W minus 1. After W minus 1, you have the uncle, which is the father's sister, right?
Daughter of his father's sister.
We already know that C minus like W inverse of W after inverse of C. We know that this gives your uncle. We already know this. If you apply your clan as the input for these 3 letters at the end here, you always get your uncle.
A man and the daughter of his father's sister. So start with the man, get the father, so it's C minus 1.
Yeah,
The sister is in the same clan as the father, so that's identity.
yeah.
But then you have to get the husband of the sister, so
Which is this
that's
W and W minus 1.
no, it's the husband of the father's sister. You're already at the sister, which is the same clan as the father, so it's W minus 1, so that's the husband of her. But
Wait.
then you have to go to the child of that's C.
Ah, okay. You don't need a W in the middle because you know that your aunt is in the same clan as your dad. I see. Oh, okay. It's because we don't need this man's uncle. We need his his cousin, which is in this case is this one. Yeah, so it's C minus 1, W minus 1, then C, maybe? Hello?
Yeah, C minus 1, W minus 1, then C.
That gives you a cousin.
That gives you your cousin of your father, which is the daughter of your father's sister. Basically, you have to prove that this is different from W, right?
You have to prove that this is different than W.
Like there are no W factors at all. Like the daughter of your father's sister, for her to be able to be your wife, then her clan must be W of your clan.
Wait, we need to prove that that gives is different than KI. No?
Well, no. In order to
No.
marry someone, for a man to marry a woman, the woman's clan must be W of the man's clan, right?
Ah, okay.
That's
That is another way to prove it. But if we prove that that operation gives Ki, then it cannot be done because Ki is the same clan as the man, and because of rule 6, that is impossible. You see what I'm saying?
Yeah.
Okay, so let me actually type that down so everybody's on the same page. So we understand that this is equal to this, right? But this cannot be equal to ki given the ki here. Because if it is, then we would be saying that you can marry somebody from your clan. That cannot be done.
Yeah, that's one point. But also, for you to be able to, for a man to be able to marry a woman who belongs to the clan, which is the output of this function, given the man's clan, right? Um, that composition must be equal to W, basically.
Yeah, actually that's pretty cool. You were going on the intentional equality and I'm going for the extensional equality. Right? That's pretty
Not
cool.
really.
Yes, really, because you're talking about the equality of the resulting function. So you're saying that this, and what I am saying is about this.
Yeah, but those are two different things, Lemus.
No, that's why I used two different terms for them.
But no. Intentional and extensional are like, okay, if you have a function, how do you define equality? Or if you have two functions, how do you define equality between them, right?
No. I'm not
Uh,
saying that. I'm not. What I'm trying to say is that you went for the comparison between two functions, the resulting of this composition in W, and what I went was, what if I apply something to this composition? What is the result of that? That's what I meant by saying extension or intention. You see, because I am applying something to the composition. You are not.
well, even if you don't, you could you could remove the application and say, okay, you are trying to argue that C after inverse of W after inverse of C equals epsilon.
Yeah, that is also a point. That is definitely.
But that's too specific. Actually, you just need to prove that C after inverse of W after inverse of C is different from W.
Yeah, but I don't know. The previous exercise we went with the ki, and to me it was easier. That's why I wanted to use ki again. To say, oh, you cannot do that because that would mean that the clan of this person is the same clan as yours, and that's prohibited, and so on and so forth. But what you said is also true, right? If you need to prove that W is must be different than this composition here, which sounds tougher to me, but who knows? If a matrilateral cross cousin may marry, then this is equal to this, which is essentially saying that the clan of my wife, the clan, yeah, the clan, the clan of my child given the clan of my wife is the same as saying what is the clan, the clan of the child, and this is what is the clan of the dad, right? Actually, this is a heavy sentence to say because they also need to be like there's there is a relationship between the clan of the child and the woman in this case. So then you can talk about the father. So C after W means I don't know. That's hard. That's hard to
Well,
think about.
well, W gives the clan of your wife, given the
Yours.
clan, given yours if you were a man, right?
And if you pass, yeah, but you were passing that to C. But C was supposed to get the clan of
No,
the
no, no.
dad.
C is the clan of the child of a man who is your wife's brother.
What? That's not what I understand. Yeah, so if you pass, if a man belongs to clan KI,
Because
okay,
like
so
you,
you're doing the bridge to the brother, to the uncle,
Yeah,
because
because like
it must be
you
the same
start,
as the wife.
yeah, if you start as your clan, you go to the clan of your wife, and then you go to the clan of a child of a man, which is the same clan, who has the same clan as the wife. That's the same saying. Like that's basically the clan of like if your wife has a brother, and that
Yeah.
brother has a child, it's the clan of that child.
Yeah. No, I see my confusion. It's because you need to the input of the C must always be a man, so you have to go to brothers. Yeah. So this is the clan of the cousin, right?
Yeah.
Okay. And what is on the right hand side of that? You have the C, so this is gonna give you the clan of the child, and you need to pass that to the invert of W.
Which
Okay?
is assuming your child is a girl, that would be the clan of her husband.
Yes. So this is saying child. Uh, whose child is this clan? That's what I'm trying to understand.
Basically, this is saying if you have if you have a child who is a woman and you have a nephew who is a man, they may marry.
No, but that is
Assuming you are
the
a man.
assumption. Matrilateral cross cousins may marry. I'm trying to understand the right hand side only of this guy. You have a child, and the child was a woman, and W minus 1 is gonna give you the clan of the dad of that daughter.
The clan of the husband of the daughter, yeah.
The clan of the husband of the daughter. This is so
Yeah.
confusing, man. If patrilateral cross cousins may marry, then C and W minus inverse of W commute. Um, so patrilateral. That's very strong. A woman may marry the son of her father's sister. Then C and W minus inverse of W commute.
Well, it's the same argument as 8, except on the left-hand side, the W would be an inverse of W instead.
Yeah, I see what you're saying. Actually, now that I think about it, being matrilateral or patrilateral matters because the system is built upon the demand. So this matters
Well,
for.
even if the system was built upon the woman, the point is that
No, it's because I
the
have the symmetry on my head and it's fucking me over.
yeah,
I,
the rules are asymmetric, right?
exactly.
The
It's fucking my head. Anyway, I think this is already enough. We already are way beyond our time. Anyway, so folks, anything you guys want to talk about before we finish for today?
I did not expect we would go into anthropology in this chapter, but here we are.
Weird. Okay, next time we're gonna talk about permutations of a finite set. Which, as far as I can tell, this isn't the exercise that we were discussing above. What happens if A is infinite or something?
Yeah.
So we're gonna talk specifically about that. Cool. Okay, finish the recording.